that much about this. Um, the thing is that when I was coerced into coming to the meeting, I looked at, what am I going to talk about? And there was this data set that had been sitting around for 15 years nearly. I thought, no, let's take a look at this and see if it's relevant. So let's go to the next slide. And I'm gonna talk about how do we look at ecosystem services, and I see this a little bit like I see my car. That's my car, and it has to deliver a service to me. Now, what would I need to do to convince you that that car works? We can look at it from the outside and say, we can classify it. It's an Audi. It's not just an Audi, it's a stuffed up Audi. So would you trust this car to give you some kind of service? If I told you that it's a 1995 model, you might, no, this is not this is not the car for you. If I told you that I rebuilt the engine, rebuilt the clutch, redid the suspension, I practically rebuilt that car except for the outside, you might say, well, maybe it's something that does give a service. And so how do we transfer this across to the way that ecosystems work? And one of the things that I'm going to talk about today is how do the rooting structures of trees work? We need to understand how that works. I haven't done work in the thicket, so I'm going to be telling you about the work that we did up in the Mapani Veld. Unfortunately, I don't have a really good photograph of a Mapani tree exposing its roots for everybody to see. And so I'm just going to start off with this camel thorn from Tswalu in the Northern Cape, because it gives a really good indication of the way that the rooting structure typically works for trees. So this is a riverbed that eroded away in a flood, and this camel thorn found its roots being exposed slowly by water washing away the sand. And what you can see is the taproot running down the middle there, and then you see these sort of what were shallow roots that went out laterally. And I'm going to talk a little bit about the function of the taproot versus these shallow roots in Mapani trees. So this is the area in which I worked. If any of you are familiar with Kruger National Park, that's the bridge across the Shingwedzi River, and we're just on the north side. And these little bossies in the front here are actually little Mapani trees. The tree that we worked on, that I'm going to show the data for, is not one of these little guys, it's a big guy. Let's go to the next slide. And this is what the site looks like in the summer when we've had a little bit of rain. And this was a monitoring project that we set up through the CSIR, and we were looking at a number of things. We were interested in how does water move in and out of the trees. And so we put these little heat sense pulses into the trees. We put them into the stems above ground, and we put them into the roots below the ground. And we put these little sensors into the lateral roots and into the taproot. And I don't know if you're familiar with the way that heat pulse sensors work, but it's 3 little probes. The middle one generates a heat pulse. And if the sap is moving in one direction, the sensor on that side will pick it up. If it's moving in the other direction, the sensor on the other side will pick it up. So you can tell if the sap is moving up or down the root. We also put into the soil a number of water sensors just to give us an indication of what the soil moisture was like. Okay, and this is what the data kind of looks like, leaping straight into this. At the bottom, we've got the soil moisture sensors, and this is over a period of about a year. So on the left-hand side, you see elevated soil moisture, and that's got to do with the rains during summer up there. Then we go into winter, no rain. Then at the end of the year, we get rain again. The sensors are at 2 depths. One is at 100 centimeters, other at 30 centimeters. And there's some interesting things there, like when you have rainfall events, you obviously wet the upper layer of the soil, but there's occasions, you can see on the left-hand side there, where the deep soil moisture sensor is showing more moisture than the surface. So you have these strong evaporative effects as well. Then the blue data set is the heat pulse sensor which went into the stem of this mapani tree. And the red is the root. And that's on this right-hand axis. And what you can see is the 0 mark over here is the transition between moisture moving up the tree or down the tree in the stem, or out the root or in the root, in the roots. Blue is the stem, red is the root. And what's fascinating is that you've got these negative values where moisture is flowing out the roots. And that, for me, did not make sense. But I suspect that the botanists look at this and say, yeah, no, we know about it. I didn't know about it. And so I'm on thin ground around botany. But just now I'll show you some isotope data, and that's where I'm more comfortable. Okay, so we've got this tree that's sucking water up and down the stem, and very seldom is it actually going negative. The blue values are not going negative very often, but red is going negative quite often. And there's a couple of little spots in this data set that I want to just highlight. The first one is what's happening around about here. Something changes there, and I'll elaborate on that. If you look very closely at the soil moisture at about that time, we start seeing that it appears as if the soil moisture increases. There's no rain, but the soil moisture seems to subtly increase down here. I was told that that's just noise. I'm going to try and convince you that it's not noise. And then there's also something very interesting happening here when the first rains come, where we see that the moisture is going negative. Okay, but as a person who's interested in the way that trees respond to moisture, one of my assumptions was, if you give a tree more water, you can have more sap flow. That kind of makes sense. That's why you water your garden. So if you don't believe that, don't water your garden. So the idea was, as soil moisture goes up, sap flow should go up. So what I've done here is plotted on the x-axis the soil moisture, and on the y-axis the sap flow. And my expectation was, on the stem or on the root, that we would have data that goes from the bottom left to the top right. And surprisingly for me, that doesn't happen. In fact, there's some really weird stuff going on. If you look at this, there's, both data sets seem to have almost like two clusters. A bunch of data points down here, a bunch of data points up there, same over here. But within those clusters, the relationship is in the wrong direction. The more soil moisture you have, the more negative the flow in the stem. And the same in the root. So this is kind of weird for me. And so I needed to unpack, first of all, why do we get this kind of identity crisis in the tree, where you either have a cluster of points down here or a cluster of points up there? What's going on there? So I'm going to focus in on a very narrow time period to be able to unpack that. And I've chosen a period of time when the soil moisture was decreasing. So in the green line over here, we've got soil moisture, times going from left to right, so soil's busy drying out. And I've got the root and the stem sap flow in blue and red. And what you see is, as time is going forward, on the bottom graph, soil's getting drier. If we look at our soil moisture plots at the top here, this is high soil moisture that's going down to low soil moisture. Time is moving in this direction. And what's curious to me is that you have that split between those two clusters of data points. As you see it especially in the root. Points down here, points up there. And so what's going on there? Now, because we've zoomed in like this, instead of plotting it as the individual measurements, I'm going to join the dots. And then we get that. And so what becomes apparent is what appears to be two different clusters of points is actually the diurnal cycle. So you've got a situation where during the day, the leaves are pumping the water. You see very positive flows in blue. That's the stem. You get very positive values in red. That's the root. But in the evening, when the leaves are no longer functional, then you just have this sort of sagging effect where the water actually flows in the opposite direction. It's not very profound in the stem, but in the roots you see this wonderful diurnal cycle where the water flows in the wrong direction at night. And if you look very closely at our green trace, you see that this is not just a little bit of water. This is enough water for the soil moisture to actually increase at night. Then during the day, it will drop down again. I don't know, can you see that in do I have to go and point to it? Okay. Yeah, okay, so if you look, there's this kind of waviness. It looks a little bit like a cross-section of a timber chip, where your water moisture is kind of, it's all going down, but it's pulsing up and down. And the down pulses, like if you look over here, correspond to when the trees are pumping. So when you've got positive flows, the trees sucking the moisture out of the ground, soil moisture goes down. At night, when things go negative, the soil moisture is on the crest of the little crinkle cut. Okay, so, alrighty. So now we know that that distribution of points that I showed you is got nothing to do with some mystical behavior. It's just the difference between day and night. And what's interesting about that to me is that the trees appear to exist in two states. You're either pumping water or you're not pumping water. Okay, let's go to the next slide. Right. Now I'm going to zoom in to the period right in the middle of the record. And this is when we're in the middle of winter. It hasn't rained for several months. And again, I've got the soil moisture in green, and this is what I was told was noise. But you see that the soil moisture is kind of low, and on this side it's starting to go up. But there's no rain. So where does that moisture come from? Is it real? Well, again, the behavior of the stems is there's a transition that's happening. If you look when the soil is nice and dry here, you see blue has got quite a high amplitude, so the stems are sucking water and dropping, sucking water and dropping. Over here, they're sucking water, drop. You know, the whole amplitude of the sap flow has changed. The same thing that's very obvious in the red, but it's a bit obscured by blue. But you've got big amplitude in the red over here, small amplitude in red over here. And so now if I plot my soil moisture versus sap flow, and I'm looking specifically at the shallow roots, what does it look like? And this is what it looks like in June. You can see that the sap flow is generally above the line. That means that the trees are sucking water. In August, we're kind of on the line. That means it sucks water, but it drops water. When we get here to September, now we're really deep into the dry season. These points all fall below the line. And when it falls below the line, it means that your sap flow in the shallow roots is negative. It means that there's water flowing out of the roots. And this is taking into account the day and night. And I'm not filtering this for nighttime. This is day and night. And practically, whether it's day or night, these trees are putting moisture into the soil. And what do we see? An increase in the soil moisture. So I don't think that it's noise. Okay. Sure. My mouth is dry. I want to then go on to another interesting thing in this data set, and that's what happens when the first rains come. So now we're right at the end of the record. Again, soil moisture is in green, so nice and dry down here. That's typical for the high-felt winter. And then it rains. Bang, there goes the soil moisture, and then it starts dropping off. Okay, what do the trees do? Well, you can see the shallow root, the net transport immediately goes negative. It rains. You've got soil moisture in the upper soil, and what does the tree do? Puts more water in there. It doesn't suck it up. And if you think I've got the sign wrong, I promise you, this is great. These trees, when it rains, they give the water away. Even the main stem is transporting water down. Okay. If we look at the soil moisture versus sap flow plots, we start off before the rain, nice and dry, so that's these points over here and over here. Immediately it rains, soil moisture goes up, we jump over to the right, and what happens to the transport? You see it all below the line, all negative. Below the line, negative. Okay, but then after a few days, and you can really count the little pulses in here, about a week after this rainfall event, you see that the blue line starts to increase and the amplitude starts to increase. And what's happened is that the tree is deciduous, it's flushed leaves, and now it's starting to pump water. And so it can start pumping the water up. The red takes a little bit longer, but eventually it starts pumping water. So these are deciduous trees that they've waited for the rain's come, there was nothing they could do with it because they didn't have leaves to pump the water, now they're pumping water. Okay, I think that that's also completely bizarre because these negative values over here, immediately after the rain, says when the first rains come, the tree puts that water into the deep soil. It doesn't use it immediately. And it may be that it wants to use it but doesn't have the leaves, but the net effect is they are putting water into the deep soil after the first rain. Okay, now we get off of the botany and into the stuff that I do. And so one of the things that we did was we collected from the trees, from shrubs, and from grasses the kind of vital bits, the live parts of the plant, and we distilled the water out of it and we measured the isotopes. Now, I can't, in a meeting like this, give you the full background on stable isotopes of water in plants. And so what I'm going to do is just present this in the manner that I would an exam for my students. Say, here is the data set. In red are the stable isotopes of hydrogen and oxygen. So your water molecule has hydrogen and oxygen. We measure the isotope ratios of hydrogen 1 and 2, oxygen 18 and 16. We plot them, oxygen on the x-axis, hydrogen on the y-axis, and we've got all our grasses plotted in red. We've got all our shrubs plotted in green, and the mapani trees are plotted in blue. Please explain for 15 marks. And the kind of thing that I would expect my students to pick up is, number one, look at all the grasses. They're sitting in this orientation, sort of bottom left to top right. And for an extra mark, the students would have to point out that that is what happens when water evaporates. When rain falls out of the sky, the data points would fall on that white line over there, which is called the local meteoric waterline. So by the time the grass gets that water, it's no longer sitting on that local meteoric waterline. It's sitting in this diagonal distribution, and that means it's evaporated water. Okay, extra mark. I would also say, if the students pointed out that where this line intercepts the local meteoric waterline, that was the isotope value of the rainfall. 4 marks. Next thing is the shrubs. They also sit on an evaporative line. And if you project that back to where it intercepts the local meteoric waterline, then it's different. Look at the mapanis. There's a cluster of mapani points down there. And they seem to be using the same source of water as the shrubs. But what's interesting is that this intercept over here with the local meteoric waterline is different from the grasses. 4 marks. Okay. The problem with this is that there's a bunch of the mapani values that are just not behaving. And there they are sitting over there. They're looking a little bit like grass. So in Walter's 2-layer hypothesis, we're supposed to get separation between grass and trees. And it was all looking pretty good until those last little bits of data from the mapanis. And so now I want to just unravel what is going on with the water in mapanis and trees, and what is the relationship that occurs between this data set and that. Okay. Now, to sort this out, I'm going to need to plot it as a timeline, and I'm going to use oxygen isotopes as my timeline. So I'm going to see how did things vary through time. And what you can see is that these Mopani values typically, it's where oxygen isotope values get more positive. That's what's going to be interesting. For the graphs, it's when the oxygen isotopes are at their negative end of the scale. You kind of get this, that's what describes this part of the graph. Okay. So this is what it looks like as a time series. Again, I've got the soil moisture and the sap flow. What I've done now with the sap flow is instead of giving you every single data point, I've reduced it to the daily flow. You know, is there a net positive or negative flow in the roots? And what we have up here in blue is the stable isotopes of water, the oxygen isotopes of the water in the Mopani. And remember I said it's where the oxygen isotopes get positive that it becomes quite interesting for the Mopanis. And you see that that's happening over here at the time that the Mopanis are lifting water. Okay, that makes sense. Look at the grasses. Nope. The grasses are plotted in red. They've got high oxygen isotope values, and they come down and they match the Mopani here at this very dry time of the year. Remember I said to you, those negative oxygen isotope values on the, let's go back. Yeah. So on the grasses, these negative oxygen isotope values are supposed to be when the grasses are using rain. Okay, go forward. Now what this is saying is that those negative oxygen isotope values are associated with the driest time of the year. There's no way that they're using rain. What they're using is the water that is lifted by the Mopanis. Okay, so there's two lines of evidence here that the Mopanis are actually lifting water. Number one, the soil moisture, which somebody called noise. Now we're seeing the water in the grass. Okay, next slide. So this is where we're at so far with the data. I reduced the soil moisture to sap flow for the shallow root to the daily net transport. So there's 365 points instead of hundreds and thousands of points. And there's an annual cycle that's taking place here. Initially, when the first rains come, we've got a period where the net flow in the shallow roots is negative. There's water flowing into the grass, into the soil. At the same time, during this banking phase, the flow in the stem is negative. So the water is flowing into the ground. And I've described that as banking. The next phase is when the water flow up the taproot is now positive, but the shallow roots are still negative. And that's where the tree is now, it's flushed leaves, it's using water, but it's using it from the taproot. Next phase. This is when it's starting to get quite dry, the tree starts using its shallow roots. And so we see in the shallow roots a little positive excursion in the transport. So now it's making withdrawals from its bank account. Next one. If we zoom in on what happens right at the end of the dry season, then we've got a situation where the flow turns negative in the shallow roots. This is right at the end of the dry season. The flow turns negative, soil moisture increases. So that's our water lifting, and the tree's now providing water for something else. Now, and this doesn't make sense. This is a system in which dry is standard. And everybody would say water limitation, water competition has to be the reason for the separation between trees and grasses. And this is saying, no, it's not. The trees and grasses are facilitating. The grass is getting water from trees. So why on earth, in a water-limited system, would trees be giving away water at the driest time of the year? Okay? And now I'm going to look at the nitrogen isotopes. So this is nitrogen isotopes measured in the little leaves, but we always took fresh leaves whenever we were sampling. And when we do this measurement, we get the percent nitrogen, so how much nitrogen is in the leaf, and the nitrogen isotopes. And what we see, I don't know, you can squint your eyes. As we go through the drying of winter, maybe those nitrogen isotopes are getting, the percent nitrogen is getting less and less. The tree is not investing a lot of nitrogen in its leaves. As soon as we start lifting water, it flattens out. As soon as it rains, there's investment of nitrogen leaves. So that's the percent nitrogen. And, I think, again, botanists would say, yes, we knew that. But I want to look at the green record. The green record is the nitrogen isotopes. Now, plants need nitrogen. If you use fertilizer, then you subscribe to that position. And where they get it from is quite important. You have one option which is very expensive, is you get your own nitrogen. That's nitrogen fixing. And the stable isotope reference that we have here is air. So if a plant is taking, if it's fixing nitrogen, its isotope value will be over here at 0. The other options for getting nitrogen are through mineralization. And mineralization says there's nitrogen that's in the soil, it's in forms that you can't use, it gets chemically transformed, and then we can use it. And these nitrogen isotope values that I have here are in the range of about 1 to 3. And if I should have put it on the slide, but if you compare that to every other plant that I've measured in the savanna, they are typically in the sort of 5 to 6 range. So in other words, these mapani trees are getting nitrogen which looks more like air than any other plant. And mapani trees can't fix nitrogen. So how are they doing this? And I think that the answer, this is speculation, is up for testing, is that when we get into the dry season, the source of nitrogen is bacteria in the soil, mycorrhizae. And what plants want is an association between the mycorrhizae and their roots. And it's going to happen in shallow roots. And so when we get into the dry season, with the mapani giving away water, it's attracting this mycorrhizal attachment to its roots. So it's attracting a source of nitrogen from the bacteria. It's giving the fungus, and it's giving up water in order to get nitrogen. The other plants, the grasses, they take this. They just, they're not, the mycorrhizae is going to be, they're also thirsty. They come into association with the grass roots, and the grass roots are competing for water. Mapani roots are giving them water. So what I see here is that the mapani has become this monoculture because of its monopoly on the nitrogen cycle. And then this gets us to some of the other things that we've done. So I've shown you how using stable isotopes of water and of nitrogen, we've got some kind of handle on how the trees are using water and how they're using nutrients. But we also did some manipulative experiments. And this was with Priyadashni Kuruganti. I practiced that. So now Priya was a PhD student, and what we did was, surrounding an individual tree, we drilled holes down to 2 meters, which is presumed to be beyond the rooting depth of the grass, put in those little conduits, and we added water and nutrients which were isotopically labeled. Now, the cool thing about isotopes is that you can add a tiny amount of water, like we added 1 milliliter or something to each of these 4 axial samples around the tree, down to 2 meters. And that's not enough water to change the water budget. The tree doesn't suddenly feel, okay, by giving me this water, I feel less water stressed. And we put in labeled water and labeled nitrogen, and we said, right, what is the tree going to do with this? And in these studies, the bottom line was, before we saw the traces in the tree, we saw them in the grasses. So that was another independent manipulation experiment using stable isotopes, which demonstrated we have a strong element of facilitation, where the trees are giving away nutrients and water to what should have been their competitors. Okay, I'm gonna finish off now, because a lot of people are interested in carbon fluxes, and just to say that at the same time that we were doing this work, we had a flux tower up in the Mapani Veld, and This is it during summer and winter. And next slide. And this is how our carbon flux has changed through time. This is not really my domain, but it was really interesting that this is a net source of carbon over the year that we monitored. And I'm going to finish there. Thank you.